Hello everyone, I am Devansh
And my name is Abhimanyu.
and we are about to present the concept of Ramdas layer, which is a peculiar aberration in the atmospheric temperature profile.
That is, the temperature minimum lies a few centimeters above the ground level. And this concept was established way back in 1932.
And today we are about to present this to our present day online audience.
And now you all must be thinking, who is Ramdas? What is Ramdas layer? And why is this concept relevant to us?
Not to worry, we got you covered. Let's hop on to find out now.
So the objective of this project is extensive understanding of the concept of elevated temperature minimum, Ramdas layer, putting forward a mathematical model to explain the concept under suitable assumptions, MATLAB simulation to plot some results relevant to the model, attempt to suggest a different analysis relevant to the paper.
Let's have a brief look at the history of this concept. 85 years ago, L.A. Ramdas observed that temperature minimum occurs 20 to 25 centimeters above bare soil on calm clear nights. German meteorologist came all the way back to India back in 1932 with his own radiation compensated thermocouple to confirm the existence of this lifted minimum. Advection was thought to be the core concept to explain this phenomenon, only to be proven wrong later on. There has been no satisfactory physical explanation for the phenomenon till now.
The phenomena was thought to be peculiar to the tropics back in 1932, and the following observations were recorded in Pune. The following plot shows experimental values of height from ground versus temperature taken at different locations in Pune. It can be clearly seen that the temperature minima occurs few centimeters above the ground, which was a surprising situation at that time.
Now we establish the problem at hand. The main objection to this concept was that such a cold layer of air above warm ground should be subject to Rayleigh-Benard instability and should quickly overturn. However, in 1993, Vasudeva Murthy, Srivastava and Narasimha proposed a model that successfully simulated the Ramdas layer on the basis of radiative stabilization.
It was particularly pointed out that the strong dependence on the lifted minimum on the ground emissivity is due to the rapid variation of air emissivity at layers near the origin. The emphasizing point is that the energy balance near the ground is rather delicate and radiation plays a subtle role. This is the principal reason why the phenomena long remained without a convincing explanation.
The following approach was adopted to solve the problem. Firstly, we established a basic heat equation defined for a particular atmospheric layer, taking into account all the radiative fluxes. Then we apply boundary conditions to our heat equation to obtain VSN mathematical formulation. Further, the equation is linearized and localized. Flux emissivity functions are also simplified and the model still stays true with negligible deviations. Governing equation is further operated upon to obtain a limited domain asymptotic solution.
Now we will explore the simplified VSN model. As we can see that the schematic diagram illustrates different terms contributing to the radiative flux at optical length u above the ground. Clearing few symbols for further simplicity. U is the mass path length of water vapor in the atmosphere. EU is the flux emissivity function. Epsilon g is the ground emissivity. F is the radiative flux absorbed by layer at optical length u above the ground. F can be divided into four parts. FVG, flux absorbed from radiations emitted by ground. FRG, flux absorbed from radiations reflected by ground. FA down, flux absorbed from upper layers. And FA up, flux absorbed from lower layers. The various fluxes have been formulated using Stephen-Boltzmann equation and some approximation.
The following linear model is taken up, where Qm is the heat transfer component due to molecular diffusion, Qt is the turbulence term which we have neglected here, and Qr is expressed as four radiative fluxes. On non-dimensionalizing the equation, we obtain the following equation.
Above flux emissivity can be simplified after using some approximations. and it can be clearly seen that in the graph, the approximated function is very close to the exact solution. In the length scales with which we are concerned, the curves almost coincide.
The following is the pictorial representation of various domains of our solution. In this plot, mu is the ratio of radiative to diffusive timescales. Here theta r is the regular solution for the bulk layer valid away from the origin. Theta I is the initial layer solution valid for t belonging to 0 to mu. Theta b is the boundary layer solution valid near ground for z belonging to 0 to root mu, while theta c is the correction factor valid near the origin.
General governing equation is transformed. T bar is converted into theta, which is our temperature function for further calculations, and new flux emissivity approximation is used for proceeding towards solution. Thetas in all the 4 regions are written and solved separately. The 4 asymptotic governing equations are given, which are solved further.
The 4 terms are expressed as power series of mu, and to obtain asymptotic limit we take mu tending to 0. Capital theta naught is our asymptotic solution, which we further plotted in MATLAB.
These are some of the graphs that we tried to produce in MATLAB. The plot on the left shows height versus temperature variation at time values of the order of mu, which are very small. The plot on the right shows height versus temperature variation at high values of t. It can be clearly seen in both the graphs the temperature minima is a little higher than the ground as expected with the existence of Ramdas here.
Our MATLAB simulation is compared with the results obtained in Ramdas's research paper. Here we can see that the plot labeled as 2 closely matches with our MATLAB simulation.
The conclusion is as follows. The radiative cooling near ground can be very large because of the extremely rapid variation of the flux emissivity of the air at short optical paths. The high gradients are due to the presence of the strongly absorbing vibration, rotation bands of the H2O molecule. This radiative cooling provides the analog of transverse side losses in the problem of heat conduction along a rod.
Further are the justifications for the approximations that we took. The value of emissivity layer length comes out to be 1.3 meter after the linear model approximation. The temperature gradient with height comes to be in the order of 0.01 Kelvin per meter, which is quite small. Hence, we are able to assume a local linear model. If we ignore the molecular diffusion term in our energy equation, we get the following term. Now, if epsilon g is 1, then lambda is 0. This gives constant temperature of Tg0 with height. Thus, we can take epsilon g to be less than 1.
While working on this project for the past few weeks, we read many research papers to get a hold on the problem in hand. These are some of the propositions that we would like to make, which we think can help in better accuracy of solving this problem. I think we can extend the analysis by including the turbulence effect or the eddy diffusion term in order to obtain the inversion curve at higher heights. The effect of the other greenhouse gases can also be taken into account for the radiative fluxes besides water vapor. The paper has taken into account 1D energy equation. We think considering a 3D analysis would have given us a broader perspective of the whole phenomena. After all, who knows if there is a corresponding Ramdas space in addition to the existing Ramdas layer.
We acknowledge the efforts and mentorship of our course instructor Dr. Rajpala. Thanks for watching. All the research papers taken up in this project can be found in the description below. Thank you.
Hope you all got an essence about the concept of Ramdas layer. The exact project report made by our team can be seen in the description below.
We have attached some reference papers in the description as well for you to delve further into this concept.
If you have any opinions on this concept, we are welcome to any of your opinions. You can give them in the comment section below. Thank you and have a nice day.